So, how can we approximate the area under the curve if it's not just nice shapes that we had? The last time was triangles and rectangles, pretty simple. Sometimes we end up with like semicircles and things, also shapes that we do know. But let's just say it's some crazy function. What can we do? Well, there's ways to approximate, and this actually gets to very applicable math, how to find the antiderivative numerically is essentially what we're doing here. So really big deal. And we're going to start off with a very, very simple concept, and that's really what it is. And obviously mathematicians blow it up later on, not talking about this class. It stays simple with this concept. So what we do is we have what's called a Riemann sum. So what if we were to break this into a bunch of rectangles? And obviously the more rectangles, if we had smaller rectangles and more of them, we can probably get a better approximation. We'll see that in one of our next lessons. But the idea right now is we're going to break it into rectangles. So we're just getting the concept down now. Later on, we're going to learn how can we make them smaller rectangles and have more of them and not really have to do as much work. So this first one is called a left Riemann sum. This one here is called a midpoint. We won't talk about that in this lesson, but in 2 lessons from now. And this one is a right Riemann sum. This is 3 of the 4. There's a 4th one called a trapezoid sum. That's my personal favorite because it's super accurate and really easy to find. Now, how do we know this is a left Riemann sum? Look at the tops of your rectangles, and what you'll notice here is that the top left of each rectangle is intersecting the graph. And for a right Riemann sum, the top right of each rectangle is intersecting with the graph. And a midpoint, it's actually right in the middle of the rectangle that's intersecting the graph. And you could see, look at the left sum. You see how it's a little bit, each rectangle slightly under the curve? Just like the right sum, each rectangle slightly over the curve. So the midpoint sum is kind of nicer because look, a little bit's over, a little bit's under, so it's probably a little more accurate approximation. So that's why midpoint trapezoid is a little bit harder to find, but they're a little more accurate. So anyways, let's talk about the left sum. If you think about the left sum, so each of these are outputs. Each of these are y values. So this would be y0, y1, y2, y3, y4, because they're vertical values, right? We're going to be looking at their heights, having to do with the y-axis. And then with the x values, so that's going to give us the length of each rectangle. Those are going to give us the heights. So what about the base? We call these delta x. So when you see delta x, they're talking about the base of each rectangle. Now, how do we find the area of a rectangle? Area of a rectangle is just base times height. So it's just going to be delta x times y0 would be this first rectangle. So for the left sum, we're going to take that delta x times y0. We're going to add it to delta x times y1. So that would be the area of the second rectangle because it has a different length, right, or height, and then so on. If we look at the right sum, same idea. This would be right here. This would be your y0. This is y1, y2, y3, and y4. So instead, this time, we're actually, instead of starting, so here's our delta x. So for our right sum, we'll call it r. We're going to start with delta x times y1. We're going to start with y1. We're going to use the right 4 values here instead of the left 4. So the right sum you use the right 4. The left sum you're going to use the left 4. So just so you notice this one started at y0. This is the very left spot. And this one started at y1, which is the second point and goes to the very end. This one will actually end at y3. It won't go all the way to y4, while the right sum will start at y1 and go to the 4th one. Notice this is just the left 4, right 4. Now we can have a bunch of rectangles. We can have like 20 rectangles, 100 rectangles, eventually an infinite amount of rectangles we're going to see in a few sections from now. And that's when things get a little more tricky. But let's just take a look at some of these problems. So we have here a table. Tables are nice, and we're going to actually break it down to a table each time. So you got to picture we're doing areas of rectangles here. So this is saying 3 unequal subdivisions. That's kind of an indicator right there. That's how many rectangles we're going to have. So we're going to break this in 3. Now, the x, the difference in the x there gives us our base. Remember, the base is lying on the x-axis. So our base is going to be 3. Our first base is going to be 3 times. Now, we're going to be doing a right-Riemann sum, 3 intervals. So what I'm going to do, this is y1, 0, y1, y2, and y3. I'm going to be using the 3 values on the right. Since it's a right sum, I'm going to be using the right 3 values. So we're going to start with, that's going to be 3 times 5 plus the next width of the rectangle is 1. Notice these widths are all changing. When we get to the algebraic ones, the width always stays the same, so it's kind of nice, but we have to plug it in, so it's a little more difficult. And then we're going to use the next y value there. Plus, from 4 to 8 is 4 times 11, this y value. So notice I just used 5, 7, and 11. 5, 7, 11, and then these are our bases to the rectangles. 15 plus 7 plus 44, and that's going to be 22 plus 44, giving us 66. Now, what if it was a left sum? Same idea. We'd use 3, 1, 4, but we'd use 2, 5, and 7 for our y values instead if it was a left sum. So this one's a left sum. 4 subdivisions. I'll just set it up, but I'm not going to evaluate. So there, that changes 2. Or I wasn't putting those in parentheses earlier. So 2 times, and we're going to use the left 4 values there. 2 times 7 plus 2 times 11. That's going to be 4 this time, plus 4 times 2. And then that's 3 plus 3 times 8. So once again, notice there, I'm using the left 4 values because it's a left Riemann sum. Okay. What about something like this? Let's break it to a table. If we're good with tables, might as well make a table, right? So approximate the area between the x-axis from 2 to 5 using a left Riemann sum. We want 3 equal subdivisions. So I'm going to break this into 3 subdivisions. So we're going to have 1, 2, 3 rectangles, and we're doing a left sum actually, so we want the left 3 points. We're not going to use this right point here. And so there's our 3 rectangles. Don't really like my shading in there, so we'll keep that there. So how do we come up? Let's just write a table for this. It's going to make things a little bit easier. So we're starting with the x value of 2, and then 3, then 4, and then 5. And then we're going to plug it in to come up with the values. So if I plug in a 2 to our function here, I get h of 2 is going to be 1 over 7 minus 2, which is 1 over 5. And then if we plug in a 3, you get 1 over 4. Plug in a 4, you get 1 over 3. Plug in a 5, you get 1 over 2. And so for a left sum, notice what's nice about these. Notice, like I said, when we get to the algebraic ones, we're just, you're realizing that change there. That's a 1, that's a 1, that's a 1. All of our bases to our rectangles are 1, so it's kind of nice. So we're going to have 1 times, we're doing a left Riemann sum, so we're going to use the left 3 values. So 1 times 1/5 plus 1 times 1/4 plus 1 times 1/3. Got to get your common denominator, so 5 times 4 times 3. That's going to be kind of nasty. That's 60, right? So that's going to be 12 over 60 plus 15 over 60 plus 20 over 60. And that's going to be 47 over 60. There's your answer. And it looks like you could probably break this to decimals, and because they're saying the approximate area. Oh, no. You're going to want to put the fraction. Never mind. They're saying approximate because this is an approximation. Same idea for this one. Just going to create that table. You're going to use 4 subdivisions. Once you have the table, it shouldn't be too bad. Let's go ahead and look at one of these. So this time they're not giving us the algebra. We're going to create a table using the graph. So pay attention to how many subdivisions we have. We got to take this from -2 all the way to 4 and break it into 3 equal spots. So that would be 1, 2, 3. And we're doing a right sum. So we're going to use this value, and this value somewhere around there. It looks kind of... So there's our rectangle is going to be touching on the right side like that. And let's break it down to a table. So -2, 0, 2, and 4. So if we plug in a -2, we get 0. Not that we need it because we're doing a right Riemann sum, right? So it's not like we really need it. Then we plug in a 0, we get a 4. Where am I getting this? I'm looking at the graph. When x is -2, our output's 0. When x is 0, our output's 4. When x is 2, our output is 6. And when x is 4, our output is 4. And then we're going to use the right 3. So we'll have 2 times 4 plus 2 times 6 plus 2 times 4 because we're using the right 3. And that gives us 28.